Hello, Ken.
Hello.
Hey. Ready? A few minutes late. And I was having connection issues. How are you?
I'm good. I'm doing good. How are you?
Yeah. And the homework was uploaded, right? I think I wrote to you. You asked for it.
Yes. Thank you so much for that.
Yeah, it's late. Okay. Any questions in general, Ken? I think.
No, not right now. Thank you.
Okay. So we have a homework. Yes, homework number 7 on 23rd, which is a Tuesday. I think we got behind by a lecture, so they're already behind. So we lost and we had more time on the graduate work. This homework got a little late, and we have midterm 2. This is going to be in class and then on. Okay. So I want to talk about small angle approximations more today and how things get simpler in that approximation. And still, there is a lot of richness left. Yeah. Often, what happens is that when you simplify things, everything is gone and it looks too simple. And in this case, yeah, I mean, there's like the nonlinear part gets away, but that also makes it unsolvable. And the linear part that is left over sometimes has sufficient richness that it is worth pursuing. And most of what happens in uh, at some molecular level shows these kind of behaviors anyway. So let's do like we did one pendulum. Let's talk about a double pendulum. Basically, you connect one pendulum to the other current pendulum, and it gets complicated very quickly. But let's do it anyway, and let's do it from the scratch so that it also serves as a practice in Lagrangian mechanics. But very soon, we will make the small angle approximation, and we want to talk about the possible modes between the two. And you had asked a nice question that if you have a spring attached to a pendulum, what happens? And that falls in exactly this category. And hopefully, I should include that example somewhere. If everything goes well, maybe in the exam, I will ask something related to that. I'll make it very clear so that it won't be too challenging. But I hope to address that, but maybe not. We'll see. Okay, so let's do double pendulum. That's going to be the example we are going to consider. So this is called double. Reasonably the same idea as before. So that's a ceiling. You have a point attached to the ceiling. And with respect to the vertical, you can have a mass M1 hanging. That's a massless rod, let's say of length A1 this time. And let's say the mass is M1. It could make an angle theta 1. And with respect to that line, the second pendulum, we can make an angle theta 2. And let's say this is angle A2. And let's not say with respect to that, let me actually give this with respect to that again. I think that's the example I keep. Does this match the figure that I have drawn in your homework? The notation for theta 2, it's not with respect to the line connecting them, right? So it doesn't matter, but it's good to keep the notation so that. Do you have your homework right next to you, Ken, by any chance?
Sorry, yes, yes, I do. That's the same.
Okay.
That looks the same, yeah.
So we are write the Lagrangian for this. So there is M1 and M2. So this time, earlier we said that we will write our equations of motion and try to get the Lagrangian out of it this time. More recently, we have been just directly doing the Lagrangian itself. So this will be X and Y stands here. So that's your X, that's your Y. And clearly the expectation is that theta 1 and theta 2 will be our dynamical variables. But for now, it is half M1 V1 square, which is X, let's say this is X1 V1, that's your coordinates there, and X2 V2. So they're temporary X1 and X2. Eventually we want probably to write it in terms of theta 1 and theta 2. So that's X1 dot square plus Y1 dot square plus half M2 X2 dot square plus Y2 dot square. That's your two kinetic energies. Oh, it's already out of the board, is it? Almost. Yeah. And you also have potential energy, which we have to subtract. Right? So that is minus of M1 G Y1 minus M2 G Y2. Right, that's what we have. What is X1 and Y1 and X2 and Y2? So we begin with that. So X1 is simply A1 cosine, no, not cosine, right? Sine theta 1. So it's A1 sine theta 1 and Y1 is equal to A1 cosine theta 1. But it's it's pointing here, so we'll say this is minus A1 cosine theta, keeping our X and Y as the usual coordinates. And this is visible, I suppose. Yeah. Okay. So that's your X1 and Y1. Let's write X2 and Y2 also. So X2 and Y2, we have to add it to X1 and Y1. So it is A1 sine theta 1 plus A2 sine theta 2. So that's our horizontal component. So that's minus A1 cosine theta 1 minus A2 sine theta. Hopefully that's clear enough. Take the dot product. It's only the theta one that depends on time. A1 is a constant. So x1 dot is equal to A1 theta 1 dot times cosine theta 1. And oh, I have to probably change the, oh, it's still in the board space. Good. And y1 dot similarly is, when I take the derivative of cosine, I get a minus sign there, so it becomes positive. So it's theta 1 dot times sine of theta 1. So that's 2 dot is equal to A1 theta 1 dot cosine theta 1 plus A2 theta 2 dot cosine theta 2. So just taking the derivatives. And here again it flips sign. So I have A1 theta 1 dot sine theta 1 plus A2 theta 2 dot sine theta 2. Hopefully that's all clear. Just writing our coordinates and multiplying it out. So the square sum of these squares. So I think I can I'll try to, when I square this and add it to this, there is a cosine square theta 1 plus sine square theta 1 that comes in. So it's just this square that comes out. But let me write that down. The added step, but probably helpful. So this is x1 dot square plus y1 dot square is equal to A1 square theta 1 dot square. That's it. That's all. That's a rise from there. And same thing with x2 dot square plus y2 dot square. These structures are there also when I square this first terms in each of this x2 and y2 dot. There's a cosine square and sine square comes in, but then there is a cross term also. So I have to keep that also. So that's A1 square theta 1 dot square plus A2 square theta 2 dot square. And then there is this cross term, which is equal to A1, A2, theta 1 dot, theta 2 dot. And the cross term is cosine theta 1, cosine theta 2, plus sine theta 1, sine theta 2. But cosine theta 1, that structure, product of two cosines and product of two sines, that's double angle formula for cosine. So that's a small simplification here. And that is A1 square theta 1 dot square plus A2 square 2 dot square, and this is A1 A2 theta 1 dot 2 dot, and this is cosine of theta 1 minus theta 2. Okay. And we already have
a question.
Yes.
How did you go from that? Is that just an angle formula?
Tell that again.
Is that just an angle formula?
Yes. Yes.
To go.
Yes.
Okay. Okay. Thank you.
Identity cosine A cosine B is cosine of A minus B.
I see now. Thank you. Thank you.
Trigonometric identity, if you want. Yeah. So, yeah, if you're, yeah, with some little, this will come again and again, so it's a good thing to keep track of. Okay. So we have, let's put this all together. We have our Lagrange UTV. Lagrangian. It is theta 1, theta 2. That's a variable. So let me not write that. So this is half m1 a1 square theta 1 dot square. That's your first kinetic energy. The second kinetic energy has this structure, bigger structure there. So it's half m2 a2 square theta. Oh, there's actually 1 first of all. So there's 1 theta 1 dot square plus half m2 a2 square theta 2 dot square. And you have half m2 a1 a2 theta 1 dot theta 2 dot cosine of theta 1 minus theta 2. And our potential energy is minus m1g times y1, but y1 was already having a negative sign, so this becomes plus m1g a1 times cosine theta. And second is plus m2 g a1 cosine theta 1 and plus m2 g a2 cosine theta 2. Correct me if I'm missing anything. Let me rewrite this, just an observation that that is an M1 and M2 comes together, right? So it's good to recognize that and explicitly write this as M1 plus M2 times A1 square theta 1 dot square. Like the idea there is that as far as M2 goes, M1 has to take the load of M2 also with it, right? So that's one way of trying to justify that, but mathematically that's what it comes. So not much you can do that. So, and then we have half M2 times A2 square theta 2. Just a small rewriting there. Two dot cosine of theta 1 minus theta 2. Here also, there is the M1 and M2 combines in one piece. It's good to recognize that, and plus M2 G A2 cosine theta 2. Not very relevant, but it's good to realize that. That's all. Okay, that's good. Okay, that's what it is at this stage. This is the complete Lagrangian. We can get the equations of motion, but we are going to be working in small angle approximation. What do you lose here? Notice that if you don't make this approximation, these are pretty much higher powers. So there is a, if you think of cosine theta, there is 1 minus theta square minus theta 4. These potentials are very highly, as far as powers in theta 1 goes, powers in the dynamical variable goes, it is a very complicated function, and it leads to nonlinear behavior. Like we are more comfortable with working with linear differential equations. By linear differential equations, what I mean is that when we have our Newton's law, we are familiar with, say, in this case, this is theta 1, right? So d theta 1, second derivative of theta 1 square plus some function times theta 1 has a source associated with it. That's a differential equation we like to work with. If this is theta 1 square here, we don't like that. Not that we don't, we don't know how to deal with it very well. That's the only point. So our technology or our mathematical comfort zone is not so good when it comes to non-linear differential equations. So whenever we work with, we want to convert things into linear differential equation. But real life, for example, this double pendulum, if you have ever seen, you will see that there is a lot of complicated structure. So you lose most of those complicated structures. So double pendulum is a nonlinear problem. You cannot predict it very easily, but in the small angle approximation, it is very dull, but predictable. Is that clear?
Yes, very clear.
So maybe a small quiz, look up a double pendulum simulation. Look up a double pendulum simulation. These days, that's very common on YouTube. And since it is so rich, you can keep watching that. Sometimes people also keep watching that. But yeah, not predictable though. So not very useful when it comes to predictability or using it for our purpose. Okay, so we are going to use small angle approximation. Right? So you want to make things linear. Small angle approximation. And our goal is to make things linear, but when I say linear, it is to be made linear at a differential equation level. That is to say the Euler-Lagrange equation level. That means since we are taking a derivative when it comes to Euler-Lagrange equations with respect to the dynamical variable itself, we can have a higher power in the Lagrangian. So whenever we make small angle approximation in the Lagrangian, keep it to order square. So keep until up to, let's say, up to theta square. So that when I take a derivative, I get at least the linear part in that. Okay, so that's a crucial point there. And if I keep that now, remember the small angle approximation is sine theta is theta minus theta cube over 3 factorial. But I want only, if I take a derivative of this with theta, I'll get a theta square. That's nonlinear. So I'll say this will be just theta. So as far as when it comes to sine theta, even in the Lagrangian, we just keep theta. When it comes to cosine theta, this is 1 minus theta squared over 2 factorial, and this will keep. So we are going to keep this approximation. Like as far as cosine theta comes, there will be theta. Notice there will be products here. There is a theta 1, theta 2. And there what we will, our notation will be is that the total product should have 2 of them. If we are having a confusion that, for example, let's say a good example here is theta 1, theta 2 times cosine theta 1, right? So that is this example of theta 1, one of the terms in our Lagrangian has theta 1 dot, theta 2 dot times cosine of theta 1 minus theta 2. Right? And if we approximate this, and this is time derivative, we just keep it as it is. We treat it as a angle variable. And now if I were to expand this out, that is 1 minus theta 1 minus theta 2 squared over 2 factorial. And surely the next one will be theta 4. That we can surely drop, but it is not very obvious that should we be dropping this or not dropping this, because if I were to take a derivative with respect to theta 1, maybe we will get some terms. So whenever in a doubt, just keep it. Right? Whenever in a doubt, just keep it and drop it in the next line. I mean, at the differential equation level, we will have a clear understanding of for linear approximation, what are the things we want to drop. So at this point, if there is any confusion, it seems to be, since we're doing it for the first time, maybe we're not sure, so then we just keep it both. But we will see that the second term doesn't come in. So it's, and this is 1 over 2, theta 1 dot, theta 2 dot, and theta 1 square. And that is minus half theta 1 dot, theta 2 dot, theta 2 square. And finally, there is plus theta 1 dot, theta 2 dot, theta 1, theta 2. Another way to see that is that in our Euler-Lagrange equation, even if I were to take the derivative with theta, then I'm left with 2 thetas, and any one theta is sufficient. Remember, we want a differential equation with 1 theta in each term. That's our goal, if you want, for linear approximation. Okay. So with that features, let's write our Lagrangian in the approximation. So I think I will go to the next board maybe, or maybe I can write it here itself. Yeah. So this is L is equal to, first few terms are already clean. This is M1 plus M2, A1 square, theta1 dot square plus and here, as I said, I think to M2, A1, A2, since I'll keep only the first term actually, even though I said I will keep it. I think it will, otherwise there'll be more steps we will have to write. So I'm actually dropping this. If there is any confusion, as I said, if you think that, oh no, this is actually going to contribute, keep it. And you will see that in the differential equation, you're getting extra more than 1 theta 1, theta 2 in each, theta 1 or theta 2 in a differential equation, and it becomes nonlinear very quickly. Is that okay? So I'm actually dropping this, okay? I'm dropping this. Is that okay? Ken, is that clear, or is there any confusion?
You're dropping it because you don't want the nonlinear differential equation, right?
That's all. But it probably is not very obvious at this stage that this needs to be dropped.
Understood.
Okay. And if that is a confusion, I'm avoiding it just to save some space and to save some time maybe. But if you think there is a confusion, you keep it and drop it at the next step.
I see.
Okay. So it should be, because the first time when you're doing it, it's probably, oh, why is this being dropped? It's not. Whenever, or for that matter, anytime, anywhere, whenever we do these approximations, whenever there's a confusion, keep it. It's an extra work, extra load, like that's what I'm trying to be lazy here, or not lazy actually. There'll be more clutter I'll be carrying around and other concepts like that. That's what I'm talking. Okay. Okay. So if you allow me to do that, so that's this. And I'm approximating M1 plus M2 cosine theta. Remember, I had to go to the next order, MGA1. This is 1 plus M1 plus M2 GA1. Cosine theta is theta 1 square over 2. So this is minus 1 over 2. Okay, so that's here. Think of this as a harmonic oscillator, right? In the small angle approximation, basically, you're approximating it like an oscillator there. And then we have M2 GA2 and minus half M2 GA2 theta 2 square. Is that clear? Any questions there? If you want, I can actually keep that also.
No questions. No, thank you.
Notice one thing, that these two are constants that doesn't have theta 1, theta 2, or theta 1 dot, or theta 2 dot. So they are just sitting there for nothing. They won't contribute to any part of the equation. You can even drop. Remember the Lagrangian, you can add a constant to that. For that matter, you can add a lot of functions to that, and still the equations of motions might not change. But this is a very trivial existence. That's just a constant. The two terms which are just constants. Okay, so with that, let's get our equations of motion. So first we do Lagrangian. This is our canonical momentum, right? So first you do theta 1 dot. So first theta 1 dot, there are two places, right? There is a cross term also. So this is m1 plus m2 a1 square and then we have theta 1 dot. And second term is plus half m2 a1 a2 theta 2 dot. I think so. And 2 is equal to m2 e2 square 2 dot and plus half m2 a1 a2 1 dot.
Excuse me, Dr. Shajesh, why did you drop the square terms on them?
Did I drop the square terms? No, I didn't.
The like a1 squared and then theta 1 dot squared, wouldn't that be on there still? Or oh, this is theta 1 dot. I'm so sorry. Thank you. Thank you. I'm so sorry.
That, yeah, I didn't understand your question, but you seem to have got the answer.
Yes, I'm sorry. My bad.
Yeah, you seem to have got the answer yourself. Yeah. Okay, if that's fine. Yeah. Okay. We also have, we need dl over d theta 1, right? That's also part of the Euler-Lagrange equation. Theta 1 has only one term contributing in there. So that's minus m1 plus m2 times g a1 theta 1, right? And same thing with g equal to minus m2 g a2 theta 2. Okay. So our equations of motion is take the time derivative of down here and equate it to that. That's all, right? When I take the time derivative, so remember our equation of motion is time derivative of d by dt of dl by d theta 1 dot is equal to dl over d theta 1. So that implies that this quantity m1 plus m2 a1 square theta 1 double dot plus Is there a 2 here, by the way? Did I miss a 2 factor of 2 here? Can we go and check that? Yeah, there is, right? Yeah. So if you go back here, yeah. So when I did this, maybe you asked me that about the cosine angle formula. So when I do x2 dot square, there is square of this, which was accommodated in this, square of this, and there is a cross term, cosine 1, cosine 2, but there are 2 of them, right? The 2 of them from here, there are 2 of them from there. So that should be a 2 times that. Is that right?
Yeah. Yeah, that's what, yeah.
That's a factor of 2 in here. And the same thing goes in that approximation. And you want to carry it through in the following steps. So this is still there. This piece is not there. Half is not there. That's only is not there. So that's half is not there. And when you do the approximation, sorry about that, but it should be not that bad to follow it through. That's not that. And here, eventually, well, this is not there, the final equation. So I removed the half from these 2 points. Okay. And then you have M2, A1, A2, theta 2 dot. No, theta 2 double dot, sorry. Theta 2 double dot, because I take the time derivative, is equal to the L by d theta, so it's minus M1 plus M2 G A1 times theta 1. The same thing for the second dynamical variable. And what we have is then you do the same thing down here, M2, A2 square, 2 double dot plus M2, A1, A2, 1 double dot. That's equal to minus M2 G A2 2. Is that clear? Notice that each of these theta, there could be derivatives, but it is linear, right? Theta 1, theta 2, theta 1. There are no double thetas anywhere, so it's not non-linear in that sense.
Just to be clear, this is when you would see the nonlinear differential equation show up, right?
Exactly. If you had a term here, for example, if you had kept a higher term there, for example, theta 1, remember if Lagrangian had theta 1 dot, theta 2 dot, and theta 1, theta 2 there, right? Then when you take the derivative with theta 1 dot, you would drop this and you would remain having this remain. When I take the dot there, each one of this will have 3 terms there, correct? You don't want that. Hopefully that helps. But you're correct, yeah, it's exactly at this point that you will see the nonlinear pieces. Okay, hopefully there was some clarification, but yes, you asked the right question, so I'm sure you understand. Okay.
Thank you.
Okay, so let's rewrite this a little bit. This is basically your coupled differential equation in theta 1 and theta 2 in the small angle approximation. Not much you can do, but you can divide it out. Let's divide it out all throughout by A1 and A2. Let's see. How do I want to divide things out? Let's see. Yeah, so clearly M2 cancels out in this term, right? That's a simple thing we can see immediately in one of the equation. And one of the A2 also cancels out. One of the A2 cancels out. And then let me divide it out by A1 and by A2 in the second equation. And in the first equation, let me divide it out by M1 plus M2 by A1 square. Right? So what I have is the first equation, I get theta 1 double dot plus, and let me have theta 1 on the left hand side and theta 2 on the right hand side. So that's M1 plus M2 divided out. So there is G over A1 remaining plus 1 is equal to, this seems to be a minus sign. And that's minus M2 over M1 plus M2. And since I'm dividing by A1 square, I have A2 over A1. And that's theta 2. Do the same thing in the second equation. I get theta 2 double dot. Bring the right term to the left, so it's plus G over A2 theta 2. That's equal to minus, but this becomes minus, right? It's minus of minus of A1 over A2. Right. Remember that the first part of the equation on the left hand side of the equation is nothing but a pendulum equation, right? If this was uncoupled, like if these two pendulums were two independent pendulums, this would be equal to 0, second one would be equal to 0. So this is the coupling kind of theta 1 and theta 2 is a pendulum, but this is getting coupled with theta 2 here. So right side is a source that's disturbing this. But whatever is the disturbance goes into here, so it's completely coupled. Theta 1 gets affected by theta 2, theta 2 gets affected by theta 1. This is very general. It is good to define some variables, standard variables in here. So let's define G over A1, right? I think I can, let's say, define few quantities. So let's say omega 1 square is equal to G over A1. So that's a natural frequency of the first pendulum, just by the length of the pendulum. That's decided. The second one, space here. Second one, let's say, is omega 2 square is equal to G over A2. Right? That's second one. Clearly, if I take the ratio of the two, so let's say omega 2 square divided by omega 1 square, then G1 and G2 cancels out, and that's A1 over A2. That shows up here, A1 over A2. Let's call that beta. It's not necessary, but it's just to combine the variables together so that we don't have to deal with so many. But
could you lower the camera a little bit?
Oh, yes. Okay. And there is one more variable, M2 over M1 plus M2. Let's call that alpha. Let me check these equations. That's pretty much what it is. So I can write these equations together as beta 1 double dot plus omega 1 square beta 1. Bring this to the left if you want, but right also is convenient so that you see it as a source. Plus alpha, and A2 over A1 is actually beta in the numerator, right? Alpha over beta and beta 2 dot is equal to 0. And this one is very similar to 2 plus omega 2 squared 2 plus beta 2 is equal to 0. Okay. That's your two coupled differential equation. Remember, this is double dot is your differential equation, right? Don't forget that the second derivative of theta 1 is proportional or is related to the second derivative of theta 2. And the second derivative of theta 2 in turn is dependent on, oh, that was exactly. Oh, did I mess up? Oh, this was 1, sorry. This is theta 1 dot. Copied it from theta 1. Theta 1. So that's what we have, and we have this second order differential equation, but we know that in a pendulum problem, or this is a harmonic oscillator, if alpha and beta were 0, or if this coupling was removed, that's a harmonic oscillator, right? Simple harmonic motion. We know that the solutions to that differential equation is sine and cosines. All right, but now this is a coupled one, so we want to be more careful. And in general, this is solved in the Fourier transform, right? So let me quickly talk about Fourier transforms a little. How familiar are you with Fourier transforms, Ken?
I know them quite well, I think.
Okay, good. So let's so then straight away we'll try to use it. So what we want to do is, this is all in time space. We want to go to the frequency space. We will work in the frequency space and then come back in it. We will have convenience in it. So just for completeness, let's say this is this is second order differential equation, right? So you shouldn't forget that. So again, just for making that very explicit, this is what this equation represents. Right? Second derivative is respect to time of theta 2 is equal to 0. T squared theta 2 plus theta 2 plus theta 1 is equal to 0. Okay, that's a differential, two coupled differential equation. What we are going to do is we're going to Fourier transform this. So theta 1 as a function of time. And the challenge with Fourier transformation is that we are used to physics happening in time, but it is usually counterintuitive, very counterintuitive, not at all trivial to analyze a motion or a system with respect to frequency. So that's the challenge. But it comes at the price that instead of differential equation, you only have an algebraic equation. So for the simplicity, you get rid of that intuition kind of. So Fourier transform will be defined as, so this is theta 1t. Instead, you ask for its Fourier transform. So this is minus I omega t and theta 1 tilde of omega. So if I know this is called the Fourier transform. If I know the Fourier transform, I know the function as a function of time itself. But this function is frequency dependent. If you want, this is breaking your function in terms of sine and cosine. Sometimes we write it as sine, sometimes we write it as exponential. As an expansion, it is convenient to write it as exponential, but what this meaning is that it is basically sine and cosines. Remember, exponentials can be broken into sine and cosines. Okay, so this is 1 or 2, so that is the same expression for 2 also. So let me not write that down again. So it's theta 1 and theta 2. What happens if I were to substitute theta 1 and theta 2 in that equation? Notice what's the time derivative of either one of this? Right, time derivative with respect to theta 1 as a function of time is equal to, it hits, this is the only place where the time is. Remember, this is frequency dependent quantity, right? And let me say, instead of 1, let me say I, right? So where I is equal to 1 or 2, either 1 or 2. So in one stroke, I can do both. Again, remember, time derivative hits only the exponential, nowhere else the time shows up. So it brings down a minus I omega. So this is minus infinity to plus infinity d omega over 2 pi times minus I omega. I'll write it on that side. That's minus I omega t. And I have minus I omega times theta 1 tilde. And let me not write the omega dependence. So that's it. Or let me write it. One is a parenthesis and one is a functional dependence, so don't confuse on that. If I do a second derivative, oh, by the way, this is theta I, right? 1 or 2. If I take a second derivative, which is what we are encountering in our problem, I take one more derivative, again it goes and it's the same time there, but it is just added. You put that in the parenthesis again. Minus omega t minus I omega. Now square of them, each one brought that down. It's theta I tilde. That should be clear. And if I were to substitute this back in our equation, what you would see is that all the terms will have an integral. So I'm going to put the integral right in the front. So this is the omega over 2 pi minus infinity plus infinity. And the exponential also is all the way in the front. And what is remaining, I'm going to write it as inside the square brackets. As a minus I omega square. So it's minus I omega square is minus square. I square is minus, so it's minus omega. square theta 1 plus omega 1 square theta 1, and I have alpha over beta omega squared times theta 2. Is that clear? I jumped a few steps there.
Yes, that's clear.
Okay. So that, let's keep going. So it's omega over 2 pi. Do the same thing for the second equation. So it's minus omega squared times theta 2 plus omega 2 squared times theta 2 and plus beta. Oh, this was plus, right? Sorry, not minus this. Oh, no, this was minus because the frequency made it. This is minus beta omega squared times theta 1 is equal to 0. Okay. Now, Fourier functions are complete functions. They form a complete set, if you want. In that sense, this can be thought of as unit vectors, right? This is a space, and in the space, each of this component, each of this function exponential should be thought of as a component of an infinite dimensional vector in that sense. So this summation is basically a long vector with each of these being components. So if that is equal to 0, that means the components themselves are 0, and that means that the whatever is in the square brackets is exactly equal to 0. So that means the implication is that this implies that omega square minus omega 1 square, I'm writing this common, times theta 1 is equal omega square, so it's a plus, so plus alpha over beta times omega square times theta 2 is equal to 0. And the same thing two plus beta. Is that clear?
Dr. Shuja, for the top term, that negative omega squared theta 1,
Huh?
why is it not positive again? Because isn't it, if it's negative I squared, doesn't that give you positive?
Negative I squared is negative I squared, right? That's minus square, minus 1 square, and I square, right? Minus 1 square is plus 1. But I times I is minus 1. Right?
Right, thank you, sorry, yes, I see that, sorry.
Complex number squared, or complex, yeah, imaginary I.
Right, okay, thank you, no problem.
And then I switched sign in the whole expression.
Yeah.
So again, to give some feel for what this is, wherever time derivative comes, that has been replaced with omega now, right? We were interested in the time derivatives, but we are going into the Fourier space. That means we are interested in omega. Omega is unknown if you want. That has the action of time derivative. And we will see that only certain omegas are allowed, and that's what is usually called the modes, and you had equation related to that. And we will see that almost immediately in the next step. And more importantly, notice instead of differential equation, we have algebraic equations now. Like this is just algebra. I can solve for omega, I can solve for theta 1. One as a function of omega. Oh, by the way, these are all tildes, right? Oh, sorry, right? This is all tilde. I've got rid of the time. This is all tilde. Somewhere I stopped dropping. Hopefully it was not too big a confusion. Okay, so okay, so let's see what we can do. Let me substitute theta 2 from one into the other. Right. So I have omega square minus omega 1 square times theta 1 tilde plus alpha times over beta times omega square times theta 2. But theta 2 itself, I can solve for using the next equation, which is gives me minus beta omega square over omega square minus omega 2 square. And that's theta 2. Right? Theta 1 tilde is all equal to 0. Are we good? So this is nothing but theta 1 can be common. So I have omega square minus omega 1 square times omega square minus omega 2 square. And then there is minus of beta cancels out. There is an alpha omega raised to 4 and that's theta 1 tilde omega, right? Remember, this was a function of omega, right? That's equal to 0. And it's completely algebraic. And here the understanding is that omega should not be equal to omega 2, right? If it is, then that denominator, then we cannot multiply by that. Or it blows up if you want. Any questions at this stage?
No questions, thank you.
Notice, remember again, and there is a similar equation for theta 2 also. Remember my theta 1 at this point, context is, remember what are we aiming for here? Our goal is to solve for theta 1, which is dependent on theta 2, sorry, theta 1 tilde. That's theta 1 tilde of omega. And remember what is this? Let's give it a if there was no if it was a simple pendulum, like, or one pendulum, let's say, not simple, like one pendulum, right? If there was one pendulum, which is how will you kill the coupling? The best way to kill the coupling is to put alpha equal to 0. So alpha, yeah, if I put alpha equal to 0, I think that does the job. So this coupling will be killed if alpha is equal to 0. There is a beta also that I don't want to put beta equal to 0 because then that would mean that one of the basically, yeah, if I put beta equal to 0, that's also another way of, because A1 is actually setting to 0. So basically, that is a non-existing pendulum. But alpha equal to 0 surely puts theta 1 is decoupled from theta 2 then. In that case, what is our solution? So if alpha was equal to 0, let's have a small digression here, then my equations suddenly become very simple, right? Omega squared minus omega 1 squared is theta 1 tilde of omega is equal to 0. What does this mean now? This means that either this is equal to 0 or that's equal to 0. If an equation is equal to 0, there are two pieces to it. Either one of them is 0. If my theta 1 was equal to 0, theta 1 as a function, that would mean that this is equal to 0. That gives me a trivial solution that theta 1 as a function of time is 0. So that's not very interesting. What is more interesting is what if omega is equal to omega 1. So this implies that omega is equal to plus or minus omega 1. That's the only two possibilities. So notice, what are we saying? We started by saying theta 1 as a function of time. You're looking for what are the frequencies that constitutes this function theta 1t. And we are claiming that, or we are concluding, at least in the single pendulum case, in the limit where alpha is equal to 0, that there are only two modes that contributes to that. Only two modes, omega is equal to plus or minus. In fact, it's not two mode, there is only one mode, omega 1, and they come in two, plus or minus. So there's a single mode that contributes to that, and you would say, if that is the case, and that is what we do typically, you would say that this is equal to, so out of this whole integral, only two of them contribute, and that's equal to exponential of minus I omega 1t, if you want, and plus I omega 1t. But whenever omega is equal to omega 1, theta 1 is not necessarily 0, right? This actually will be a constant. That constant, you would say, is A and B, right? With the integral term there for the dimensions and other things. Or you can say, exponentials can be written as cosines and sines. You would also say this is equal to maybe A prime, another constant, cosine omega 1t plus B prime sine omega 1t. Either you say this is the solution or that's your solution. So once I get my modes, what are the frequencies that are allowed, I just go into that integral and read out that, only those modes contribute, so my solution will be of this kind. Is that clear, whatever I'm saying?
Yeah, very. I am curious about the A and B though. You said they came from where again?
Okay, so here, if omega was equal to omega 1, maybe, elaboration here, right? So I kind of verbally said it, but if you want to make it algebraically more precise, this is just a concept. If omega was equal to omega 1, what is theta 1 tilde? See, we are interested in theta 1 tilde, not in omega. So what is theta 1 as a function of omega? Notice it has solution only for omega equal to omega 1. That means to suggest that that's a delta function. If you want to write it as a function, this could be plus or minus. Right? So there is two solutions to this, plus and omega plus omega 1. Right? Omega equal to omega 1, omega plus omega 1. And then you say, what about this? What is this equal to? There is some coefficient in here, right? I don't know what that coefficient is, since because when omega is equal to omega 1, theta 1 could have anything. Right? So you say that I don't know that, but it could be anything. So let's say this is A, and that's your B. Okay. Like this function has only two modes, that's omega equal to plus or minus 1. This says that omega is equal to omega 1, and this says that omega equal to minus omega 1. And in front, it could be any function, but not a function of omega, because at that point, with the moment you set omega equal to omega 1, this is only a function of omega 1. Is that clear?
I say yes, thank you.
If that is the case, I substituted that, put it back in our function. Theta 1 t is equal to minus infinity to plus infinity d omega over 2 pi e raised to minus omega t, and I substitute a times delta function of omega minus omega 1 plus b times if that is the case, then our solution is, remember the delta function integral, just multiply it with, do the integral and replace all the integrals with omega over omega 1. And remember, since this was a function of omega, this could be function of omega. It's not very relevant, but if you want, you can keep that as a whole thing as a function of omega. So when I do this integral, this is 1 over 2 pi times exponential. So this is a of omega 1 and e raised to minus I omega 1 t plus d of minus omega 1 over 2 pi. Those are just constants. Whatever this is, this depends on omega 1. That's just a constant. So I can call that A or B. And in fact, if you want to write this as sine or I'll also at this stage write it in terms of sine and cosine. And you can say this is A prime times sine omega 1 t plus B prime times cosine omega 1 t. But either way, I don't know this A and B, remember that. Right? It's not that I know what is A and B, I don't know, but those are fixed using initial conditions, correct? Like if it was a simple pendulum, these gets fixed with using the initial condition. I need to know what is theta 1 as a function at t equal to 0 and theta 1 dot at t equal to 0. And that fixes that, correct? Or in a simple pendulum. Is that very clear? Because now we are going to do the same thing with double pendulum. This one, alpha equal to 0 approximation.
Yeah, that was very clear. Thank you.
And I noticed that it is time. So yeah, it's a good place to stop. Maybe you can attempt on trying to solve that. Now it's a quadratic equation. It's not actually quadratic, it's a omega raised to 4 equation algebraically. So there will be 4 solutions instead of 2 solutions. Right? You can try to attempt that and try to do this in the bigger case, but we'll do that in the next class.
So you just perform the same thing with theta 2.
Oh, no, not theta 2. This is, no, not that. No. So notice that this is alpha equal to 0.
Oh, yeah, I see.
This is too simple. This is pendulum. This is simple pendulum. We have to do this for alpha not equal to 0. And that makes it a lot more complicated. This will have 4 solutions. Like now this is A, B. In our coupled case, there will be A, B, C, D. There will be 4 of them. Like 2 modes, but each one comes in plus or minus. So there are 4 of them. Okay?
Okay.
So we'll see that next time. I wanted to go over this slowly. Even though all the algebra, everything is straightforward, it is good to go over the. Okay.
Okay, thank you so much.
Yeah. Thank you.